welcome to Oddly Real. I'm Nem Stefanovic. Our universe is immensely vast. Traveling at the fastest possible speed, which is the speed of light, would require over 4 years to get to our nearest neighbor star, Proxima Centauri. Traversing our galaxy, the Milky Way, would require over 100,000 years at this speed. Our observable universe has a diameter of over 92 billion light years, meaning we need at least 92 billion years to traverse this distance. The prospect of traveling any significant distance through this vast cosmos seems daunting. Yet, there is an intriguing possibility that nature, or human engineering, might allow for the construction of a shortcut through space-time between distant points. We call this a wormhole. Wormholes have not been observed, but the laws of physics predict their existence. In this episode, we will explore the science behind wormholes, the challenges in how they're created and kept stable, and even their implications for time travel. I want to start by saying that wormholes are presently theoretical, and they have not been accepted to firmly exist by the scientific community. We should be clear what we mean by theoretical. Theoretical does not mean that wormholes are simply imagined without a basis. On the contrary, there are very well-known laws of physics, in particular Einstein's field equations, which describe the curvature of space-time in the presence of matter and energy. These are very real and have been firmly accepted by scientists for well over a century. Using these equations and rigorous mathematics, wormholes are predicted to exist with a few challenges and uncertainties. The reason why wormholes are not concretely established as real is because wormholes have not yet been observed, and there are open questions about their stability. A wormhole is a pathway between 2 points in space-time through hyperspace. The easiest way to explain this is to imagine a simplified 2-dimensional space rather than our familiar 3-dimensional space. Space could have folds so that it's not perfectly flat. These folds could result in regions of space that are normally separated by vast distances being very near each other through hyperspace. Hyperspace consists of additional dimensions of space beyond our familiar 3 dimensions, but outside of our universe, which is not normally accessible to us. However, it may be possible to curve space from one region into another to create a tunnel. The distance separating the 2 regions through the tunnel could be a very short distance, like a few kilometers, even though the regions of space are light years apart outside of the tunnel. This structure, which consists of 2 mouths and a throat, is called a wormhole. Note that wormholes are not only able to connect 2 points in space-time within our universe, but possibly across different parallel universes as well. There are many solutions to Einstein's field equations that have predicted the existence of wormholes, such as the Einstein-Rosen Bridge. The idea was that a black hole could act as a mouth of a wormhole at one end. The other end would be connected to another unusual and highly speculative object known as a white hole. A white hole is a theoretical object that is essentially the opposite of a black hole. This is an object that would expel its contents and nothing would be allowed to enter. The 2 mouths could be connected together such that the black hole would act as an entrance and the white hole would act as an exit, and the combination would eliminate the singularities within to create a space-time tunnel instead. This is an example of a one-way wormhole in which you can enter one side but not the other. However, this type of wormhole is considered non-traversable. The tidal forces within a black hole grow without bound as we approach the singularity that would rip apart any material objects as they come near. Additionally, black holes are continually being exposed to high energy radiation, both from external sources but also from vacuum energy fluctuations. The black hole's gravity accelerates all incoming radiation to enormous energies that would destroy any material object that tries to traverse any tunnel within. Finally, the theory does actually predict that a bridge would open up to avoid the crushing effects of the black hole singularity, but only for a fleeting instant. The wormhole instantly collapses and does not permit the traversal of anything through it. Alternatively, another wormhole solution was found that involves a spinning black hole. It is very common that celestial objects, like stars, have a spin. When objects shrink or collapse, the rate of spin increases, much like a figure skater spins faster when they pull in their arms. It is predicted that a spinning star that collapses into a black hole can spin at enormous speeds. When a black hole with spin is analyzed, we discover that it possesses a singularity that is not a point, but a spinning ring. It may be possible to traverse through the ring to enter into another region of spacetime. What's interesting in this case is that this type of black hole permits physical objects to traverse through the ring singularity without being crushed by gravity. However, it still suffers from many of the issues that other black hole type wormholes experience, including exposure to extremely high radiation, and questions about the instability of the passage through the ring. The other problem with trying to predict the behavior of wormholes using black hole theory is that we just don't know enough about the laws of physics in the extreme conditions around a singularity. Many of the mathematical predictions grow without bounds, such as infinite tidal forces. These infinities are indications that new physics is required to describe these situations, such as those of the not yet fully understood laws of quantum gravity. More recent wormhole solutions to Einstein's field equations have been found that allow for a two-way traversal from either mouth. In this case, the wormhole would appear like a window, where someone at one end of the wormhole would see the light and imagery from the other end of the wormhole, and vice versa. For example, each mouth could appear as a sphere in our 3D space. How would a wormhole even occur in nature? Studies of wormhole evolution have been done for perfectly spherical wormholes. The process involves two singularities connecting together across hyperspace. They meet and annihilate, which then produces the wormhole tunnel. The tunnel grows in circumference, but then begins to retract and pinch off again. The entire process happens extremely briefly, such that nothing could pass through the tunnel. The wormhole is inherently unstable. Also, how would two singularities naturally find each other through the vastness of hyperspace to create a wormhole? This is unknown. Is it at all possible to create a stable wormhole which doesn't immediately collapse? Interestingly, more recent insights have shown that a wormhole can indeed be made to be stable so that it is held open. This requires the use of some kind of a material that can push the walls of the tunnel apart so that they don't contract. Specifically, this material would need to be something with an average negative energy density, something that would be able to provide a gravitational push outward. We call this kind of material exotic. Light that passes into this wormhole would emerge being spread out or defocused rather than concentrated together. This is the opposite effect of gravitational lensing, where light is focused around a massive object like a star or a black hole. This also means that there is a real measurable way to detect this effect, although no such object with this defocusing characteristic has been found. So we need an exotic material with negative energy density to effectively repel the walls of a wormhole tunnel to prevent it from collapsing. But what is this exotic material, and is it even real? Average energy densities of material that we encounter in nature are positive. Yet, interestingly, there is in fact a real phenomenon with negative energy density that has been identified. It turns out that in certain circumstances, vacuum fluctuations, which is the random borrowing of energy between fields in space and governed by the uncertainty principle, can be exotic. Normally, vacuum fluctuations like those here on Earth have a zero average energy density, since they spend an equal amount of time having negative energy as they do having excess positive energy. However, in curved spacetime, there are many situations where vacuum fluctuations can indeed have negative energy density. For example, the vacuum fluctuations near a black hole's event horizon have an average negative energy density and are exotic. Could there be circumstances where vacuum fluctuations with negative energy density hold open the wormhole? It's not clear. We are able to actually calculate the amount of energy needed to construct wormholes of a given size. For example, in order to create a wormhole that is 1 meter in size, it would require the mass equivalent of Jupiter, but in the form of negative energy. There's still another very interesting situation involving wormholes that is worth mentioning. Much like a vacuum exhibits field fluctuations, the same is true with the gravitational field and space-time itself. The smaller the region of space, the larger the experienced vacuum fluctuation. If we were able to peer into scales at the size of the Planck-Wheeler length, or 1.62 times 10 to the power of minus 35 meters, the fluctuations are enormous, to the point where space is described as boiling, or taking on a kind of quantum foam structure. Interestingly, this is happening everywhere throughout space, from distant regions of the universe to the room in which we're present here on Earth. At this scale, space does not have a definite topology or geometry, but instead takes on a range of probabilistic structures. It is here that space could also contain tiny subatomic wormhole structures embedded within it. Clearly, these wormholes would be too tiny for practical traversal, but it begs the question, could a sufficiently advanced civilization be able to capture such a wormhole and scale it up into something at a macroscopic scale? Again, it is not known. What if we wanted to build a wormhole ourselves? Perhaps one day human civilization will be sufficiently advanced to construct our own wormholes. Is it possible to build a wormhole? Classically, the process would work by either identifying regions of folded spacetime or folding spacetime ourselves. Spacetime is a kind of entity which distorts and even twists in the presence of matter and energy. Given enough mass or energy, spacetime can be manipulated. One way would be to create a singularity that would create a deep, narrow connection to form a tunnel between two spacetime regions. The regions could be either in our own universe or possibly across parallel universes. In fact, any object could be compressed in theory with enough energy down into a singularity. For example, our sun would need to be compressed into a 2-mile diameter to form a black hole. A mass equivalent to a human body would have to be compressed down to a subatomic level to produce a black hole. The only natural way to achieve this level of compression is through the collapse of a massive celestial object, like a star, to produce a black hole. But an advanced civilization may wield enough energy to manipulate space-time using atomic collisions or concentrated beams of light or some other yet unknown means. Finally, it is worth noting that wormholes are not just mechanisms for traveling through space, but they can also be used to travel through time. Oddly, the passage of time through the wormhole would be experienced differently than the passage of time outside of the wormhole. For example, imagine two people communicating with each other through a wormhole, but also standing close to each other in the same room of a house. They would see each other, and any clocks between themselves tick away at a synchronized, predictable rate, both when looking through the wormhole and when looking at each other from outside of the wormhole. Yet now, one of the individuals takes their wormhole onto a high-speed rocket ship and travels at close to the speed of light for 10 years relative to Earth's time. Both individuals looking through the wormhole would see each other normally, with both of them experiencing the same passage of time. However, when the person that stayed behind now looks outside of their wormhole into the room, they don't see anyone there. The rocket traveler has left for their journey and won't be back for 10 years. When the rocket ship traveler returns, They look at their friend who is waiting in the room and see a 10-year older version of that person that stayed behind. The rocket traveler has not aged much due to their high-speed travel and the laws of relativity. Yet, when the rocket traveler looks through the wormhole, they see their friend who stayed behind looking like the younger version of themselves. The wormhole has become a time machine. Either individual could now go into the rocket traveler's wormhole entrance to travel 10 years into the past. However, they could not travel to a time before the time machine was created. On that note, we'll end our discussion of wormholes here. I hope you enjoyed this episode, and remember, oddly real, really interesting.